Chapters 11 and 12 and 13 for that matter, all about waves. And as we talked about in class, this is a railway in New Zealand after a 7.1 earthquake. And clearly the train is going to have issues going along here because the earthquake had caused the ground to shift, and you can see the change in the course. If you're interested in something like this, and go to Google and whatnot and search earthquake damage, and you can see all kinds of cool things of creeks and roads and railroads and things like that that are shifted because of earthquakes. It's kind of neat. Let's look at waves. Properties of waves. First we have to say, what is a wave? Well, a wave is actually a disturbance in a medium. A disturbance, of course, you can talk about as energy pulsing through the medium. But first we need to say, what is that? Well, a medium is the material through which a wave propagates. Most of the time we'll be talking about air when we talk about sound as a medium, or you could be talking about water if you have a water wave going through there, or even if you feel a wave traveling through the ground through an earthquake. The medium would be the ground. What's a disturbance? A disturbance is external energy to the system that has been introduced to the system. So, you want to see a water wave. You have a calm pond and you drop a stone into it. You'll see ripples form because that stone has added energy to the pond, and the energy from that stone entering the pond causes the ripples. So that's what you see there. This, of course, you can think of the ballpark wave. It's an analogy. It's not a real wave. But what happens is the disturbance is some good play in baseball, and the people all stand up and cheer together in an organized fashion. Examples: sound, light, water droplets in a pond are all good examples of waves. In space, no one can hear you scream, and the question is, why not? Well, if you'll recall, sound is known as a mechanical wave, and mechanical waves require a medium to propagate. So the question is, can an astronaut still communicate with the shuttle? The answer is yes. Radio is a non-mechanical wave, and it does not require a medium. So mechanical wave being the big idea here, they need a medium. Sound needs a medium. Earthquake needs a medium. Radio, light, X-ray, gamma rays, and stuff do not need a medium. Wave anatomy. So we need to talk about a few different parts of waves. First of all, we have a trough. The trough is the bottom of a wave. Crest is the top of the wave. And you look here, this little bar signifies a wavelength. That's the little Greek sign, lambda. It's kind of like an H that gets sat on by an elephant. This is a wavelength. That's a wavelength. That's a wavelength. Any point at which you can go an entire wave is a wavelength. We have two basic types of waves. We've got longitudinal waves and transverse waves. A longitudinal wave is a wave where the motion of the wave is parallel to the direction of the motion of the particles. Think of a spring. The spring is compressed and stretched as it vibrates, back and forth, back and forth, back and forth. You can see this pulse of compressed, stretched, compressed, stretched, compressed, stretch. That's longitudinal. The wave is moving across the screen. The particles are vibrating across the screen. A transverse wave, on the other hand, is a wave where the motion of the particles is perpendicular to the direction of the motion of the wave. The wave is moving across the screen, but the particles are moving up and down, up and down. Examples. Longitudinal waves, a good example is sound itself. Sound is a very good longitudinal wave. The air particles that are vibrating at your voice box, for example, vibrate the ones next to them, and they vibrate the ones next to them, and that vibration travels through the air, through particle to particle, towards whoever's hearing that sound. A transverse wave, on the other hand, a good example is things like light. Light is as a wave travels up and down like this. Equations. Period T, capital T, is the time of one cycle, and frequency is how many cycles per time frame. So frequency is 1 over the time. So if your frequency is 1, it's 1 over a time that it takes to do it. Frequency is measured in hertz. Hertz is cycles per second. Period is measured in moments. So let's look here. If we have the classical velocity equation, where velocity equals distance over time, and if we do a little substitution, velocity is equal to lambda, wavelength, which is our distance, over t, period. And we could also kind of substitute these guys around, and we end up with this. Velocity equals frequency times wavelength. So here is the main equation, right there, main equation. So now it's time to practice using this equation. So let's dump a little paint. The homework will be located on 383, and that's 1 through 4.